Hello, in this video we're going to be taking you through the data assumption checking for the standard multiple linear regression that you produced. With this, I think it's helpful to remind ourselves of what kinds of variables we were looking at, what our hypotheses were. Our first hypothesis is very much about how each of our predictors comes together to help us understand scores on a measure of cognitive well-being. So we're interested in gender, which is a binary variable, dichotomous variable, and then importance of materialistic aspirations and the attainment of materialistic aspirations, which were both continuous variables in this example. And then we go on to make some more specific hypotheses about the relationships between some of the predictors when we've controlled for the others, so that there'll be a positive relationship between attainment of materialistic aspirations, and that there'll be that male participants will score higher on the measure of cognitive well-being than female undergraduates after we've controlled for importance and attainment of materialistic aspirations. So those are the kinds of things that we wanted to look at using the hypothesis. Using regression. So this is the output that we produced. And it's important to remember that there's a lot of debate in the literature about how best to test the assumption of normality with regression. But the assumption is actually that for each level of your independent variable or variables, the outcome will be normally distributed. So it's not that your outcome variable itself on its own has to be normally distributed, or that any of your predictors have to be normally distributed. You should go through and check to see if there are any really extreme scores to start with, just to make sure that kind of you understand what's going on with the data and that there aren't any data entry issues. But the assumption of normality is about really the residuals in the model. So in the examples for the ANOVA and the MANOVA, I showed you the traditional approaches to testing the assumption of normality using the raw data, but I explained that there's a more contemporary approaches to looking at normality in those contexts using the residuals, the error in the models. And that's actually what we've been doing with the regression for a long time. So it's the same principles. They're all actually related techniques, which is why you can explore the assumptions in the same way. I would have a look at the blog that I've put a link to in some of the slides about that, and also the paper about testing assumptions in ANOVA using residuals for a bit more guidance on that as well. So the first thing that we should do is really look at the mean scores of each of the variables. Now in this we've taken quite a traditional approach again, and we haven't transformed our continuous variables in any way. If we find that we have some issues with things like independence, if we could test for that, if we found that we had some issues with non-normality, with really highly correlated predictors, multicollinearity, all those sorts of things, then actually one of the ways of dealing with that, which can be quite successful, is to mean center our predictors that are continuous before we add them into the regression. So if you have some issues within the interpretation with the a 0 score on one of these doesn't make sense. I think actually a 0 could make sense on these in some respects. If we find that we violate some of those assumptions, then the first thing I would try is to mean center my continuous predictors to see if that overcomes the issue. If not, then there may be more radical transformations that you have to think about doing. But to start with, we'll look at the mean score on each of our variables. So we can see the mean score overall on our outcome variable, cognitive well-being, is 3.2. The mean score for sex doesn't really tell us much, so we can ignore that. It's and then the materialistic aspirations, it tells us that the mean score is 4.0, and the materialistic aspiration attainment is 2.8. Okay, so we're getting a sense of what's going on. We've got 178 individuals in our sample, and we know that we don't have any missing data, so we don't have to worry about how that's handled. because we haven't got any, so that's fine. If you did have missing data, then you would need to think carefully about what you do with that in the regression. The two main approaches are listwise deletion or pairwise deletion, and whichever of those you take has implications for how you interpret some of the information that we've requested from the regression. But we don't have any missing data, so that's not an issue here. So the first assumption I would want to check is about the way that all of my variables relate to each other. Now it's a bit more tricky to explain the relationship using a correlation with the dichotomous variable, although technically it's a special case, you could, but we'll ignore that one for now. What we're interested in are the way, in particular, our continuous predictors relate to each other. And what we don't want to see is that those predictors have multicollinearity, which is where they have a very strong correlation with each other, which is sort of 0.7, 0.8, 0.9 correlation coefficient. That would be potentially problematic. What we can see is they do have a strong relationship, but it's not too concerning. So, 0.5 is a strong correlation, but it's not really strong. So that isn't too concerning, but we can double check whether we have multicollinearity using our VIF and our tolerance values, as we did with our MANOVA. So we will look at that in a moment. The other thing we want to see is whether our predictors have some relationship with our outcome, and ideally what we'd like to see there is kind of moderate to strong kind of relationships, really, correlations. If we have really weak correlations with all of them, some people would argue that you shouldn't be doing the regression. You should just stick with the correlations. But I think the argument against that is that sometimes it's about looking at how these things come together to predict an outcome score, not just individually controlling for each other. We want to know how, when we look at them in combination, do they tell us something? So the cumulative effect of our predictors on predicting our outcome. And in particular, one of our hypotheses was about that. So it makes sense, even though we have fairly weak correlations between each of our predictors and our outcome here, based on Cohen's rough guidelines of weak, moderate and strong correlations, I would make the argument that to still do the regression, because you want to see how they come together. And you can have situations where one predictor actually masks the effects of another, and it's not until you get them into the regression that you start to see that. So looking at this table, I think that there aren't too many concerning issues here. But let's double check that we don't have multicollinearity by looking at the table of coefficients and our tolerance and VIF values. So if we had any VIF values in here of greater than 10 or any tolerance values of smaller than 0.1, we would have an issue and we'd need to deal with it. One of those is might be, as I said, to try and mean center everything, continuous variables. That can help. If that doesn't work, then it can be a case of perhaps developing some sort of composite score. So it might be that actually we could multiply the importance by the attainment in some way and create a product term, so we only have one variable that we would enter that would be meaningful. That's not always the case in all scenarios. So it may be at this point, if you have a real problem with multicollinearity, then you would just split them up and run separate simple regressions instead. That's another approach as well. In this case, we can see we don't have any issues with multicollinearity, so it's kind of safe to proceed. So I'll also just look at, when we produced this regression, I did ask for the Durbin-Watson to be produced. Now, the issue is with this, we have no idea, because this is someone else's data. They didn't have an ID variable. There was no way of knowing that the order in which we saw the data when we received it was actually the order in which it was collected. And so really the Durbin-Watson is meaningless. It's completely dependent on the way that the data is organized in the data set. If we do know the order of in which the data was collected, then it's definitely worth doing your Durbin-Watson. So I produced it here just so you can get a sense of it, but actually in this example we wouldn't be able to use it. But if we did know the order in which the data was collected, and we got a value of 1.4, then that is moving away from that ideal of 2, where we don't have any problem at all with independence. But actually, for Andy Field, it's within the ranges that we can cope with the regression. So if it's within 1 to 3, the Durbin-Watson can only vary from 0 to 4, but if it's within 1 to 3, then it's not too concerning. As soon as that value is less than 1 or greater than 3, we have a real problem, and we're going to have to do something about it. But as I said, one of the ways to combat that is actually to mean center your continuous variables, and sometimes that corrects for the issue. So that is a useful way of, and it actually can sometimes improve the interpretability of the actual regression, whereas some of the other transformations you can do make it so much harder to interpret. So that's a good sign as well. So next what we'll start to do is look at things like our normality, and we'll also look at linearity, something called homoscedasticity, or and the alternative when you've got a problem is heteroscedasticity, but we'll look at all of that in a moment. So the first thing I want to do is to look at whether we might have any really extreme multivariate outliers. So a multivariate outlier, if you remember from your regression lecture, is where we have a strange combination of cases across the variables. That means that someone scores very differently when we look at all of the predictors and the outcome in comparison to others. So one of the ways to do that is to look at the maximum Mahal distance. And if you look in Julie Pallant's book, or if you look in your regression lecture slides, there's a table that you can compare that against, and it would give you the maximum Mahal distance that we can have without any outliers being present. And I think for something like 3 variables, 3 predictors, it's something like 16. I can't remember off the top of my head, but so it looks like we probably have at least one Mahal distance, at least one multivariate outlier. We can actually identify how many we have by looking at the data set and using the newly created Mahal distance variable in our data set to sort the cases and identify which variable or variables are the potential outliers. I'm a little bit lazy, so what I tend to do is I look at the Cook's distance first before I do anything else, and the maximum Cook's distance can tell you whether, okay, well, we may technically have some multivariate outliers, but are they causing a problem? Are they exerting what we call an undue influence on the model? Are they pulling the slope of the regression line so far away from the rest of the data points that it's having a detrimental impact on our outcome? So the Cook's distance, if that is greater than 1, the maximum Cook's distance, we have a problem. We're going to have to do something about it. In this case, it isn't. So I say that even though we might have technically some Mahal, the Mahal distance suggests we have technically some multivariate outliers, they don't appear to be swaying our model too substantially. So actually, there's more of a case for including them than transforming them or removing them. So I would use that to argue that actually, no, it's safe to proceed with those potential outliers intact. But again, if we did find that there was an issue, we also have a Cook's distance saved in our data set following the regression. We could sort the variables based on that and pluck out the cases that are causing the issue and rerun the analysis and see what happens. And that's the best practice. And then you would compare the 2 outputs. If there isn't a massive change between the first and the second output, then you can make the case to just keep the original, that the outliers, you investigated them, and they don't appear to be causing too many issues, therefore you've retained them because they could represent real world data, then representative of the population, so you want to include them if you can. So those are what we would use from the residual statistics. The next thing that I've produced here, which the standard approaches, the traditional approaches, would just really ask for this plot here. So this may be, based on the walkthrough, the only one that you've generated. What we're looking at here is the standardized predicted value for each individual against essentially the observed value. So it's the residual. So how far away from the actual predicted value our actual observed value for each individual was. And the reason that this is traditionally used is because it allows you to test normality, linearity, and homoscedasticity all in one go. So if we have absolutely no problems with our data, then these residuals will be in a kind of rectangular shape across the entire range, and the tails then would be symmetrical, and that would suggest that we've met all of those assumptions. If we have an issue with normality, or then we start to see some shapes forming in here. If we have an issue with linearity, then what we'll see is some really clear curves, or an S shape. Now, it may be that there's something potentially going on here, but that might be because we've got that dichotomous variable. It's not too concerning. And you'll see what I mean when you look at your scatter plots about that. If we have a really clear funneling effect, so that you've got a much wider spread of data points on one end of the graph compared to the other, then what that suggests is you have something called heteroscedasticity, which is where the model is much better at estimating scores at one end of the outcome variable than at the other end. So it's really accurate, say, at predicting scores lower on in cognitive well-being, but really poor at predicting scores at the higher end of cognitive well-being. That would be a problem. It suggests that actually one of the main causes for that, and for the independence issue, is that you've excluded a really important variable that's influencing the results from the analysis. So sometimes a way to fix that is to look back through the data and see if there's an additional variable that you think actually theoretically should be included in the model that you didn't initially. That's unlikely, because you should have thought about that really carefully before you collected the data and before you entered it, but it can happen. If you've got a problem with a curvy linear relationship, again, it depends what's going on. It may be that if you mean center the variables, that might help with it. It could be that there is an additional variable that should be included, or it may be that's just the nature of the relationships between the variables. And if that's the case, you can look at things like transformations of the continuous variables, but they can, other than mean centering, but they can cause new problems even if they fix the old ones, which they don't always. But it may be that if you really can't fix the issue with linearity, then you might need to explore alternative approaches to modelling that. There are curvy linear estimate regressions and things out there that you can use, but they become more complicated to use. So really the issue with linearity is quite fundamental. But the first thing to try is that mean centering of your continuous variables, and that can sometimes fix the issue. If we have an issue with normality, what we'll tend to see is that we'll have the tails of the residuals coming out potentially kind of a different, they're not symmetrical. So for example, and we've got that potentially slightly here, but actually normality can be the hardest one to assess using this graph, which is why now that we have this option, we can ask for a plot of the standardized residuals, and we can test normality much more clearly using this. What we can see is, we do have some skew, which is what that overall scatter plot suggested, but it's not too substantial. You can see it's roughly following a normal distribution, and if we have a decent sample size, which we do, over 100 here, then actually the regression can be fairly robust to moderate violations of normality. So we should be safe here, and that's what the PP plot also shows us. If we had a perfectly normal distribution, every one of these data points would fit in the line exactly. We can see some deviations away from that, but that's not too extreme, so that's a good sign. When I talked about this kind of potential curvy thing going on here, and how that might be to do with one of our dichotomous predictors, when you look at the plots between well-being here on the scatter plot, you'll see that obviously you've got males and females, and you'll get a sense of kind of where people fall within those, but it's less helpful to explore using the scatter plot in that way. Another way of checking for linearity, as well as to find some evidence of the linear correlations, which we did earlier, would be to look at whether we have a nice clear trend on a scatter plot between the each of our continuous predictors and our outcome. And it doesn't look like there's an awful lot going on here, to be honest. There could be a couple of outliers here, but nothing too extreme. But it looks like actually you probably haven't got too much going on with either of these individually and our cognitive well-being. So overall, it suggests that we've met the assumptions substantially enough then to go on to warrant the interpretation of the results. I think potentially what I might do, because we don't know about independence, is to mean center the variables and rerun the analysis anyway to see if that improves any of the issues, and because that can be quite a good way of guarding against independence. If we really don't know the order in which the data was collected, that could be another way of making the analysis more robust. But there are some really good blogs like Statistics How To that talk through, or the analysis factor, that talk through when you would want to mean center and when you don't want to mean center your variables. And those are the links are provided in your regression lecture. So have a look now at your actual results for the ANOVA and see what, for the regression, and see what you think about it, and then watch the video where we talk through again the interpretation of the regression itself. Thank you.